Hello, everyone. Welcome back to the AAS YouTube channel, and this is the good stuff. This is the AAS Author Journal Series, and I'm super happy to have Rosa Wallace Everson with us today. Hey, Rosa.
Hi, Frank. Thank you for having me.
Oh, well, thank you so much for doing this. It's a really lovely paper. Where are you at? What's your geolocation?
Well, I'm usually in sunny Santa Cruz, California, but right now I'm in North Carolina because I got evacuated due to wildfires. So I'm lucky to be staying with family right now and continuing from here. It's COVID time, so everybody's doing it.
It is. So you're a grad student at Santa Cruz, right?
That's right. I'm about halfway through my PhD, so I have about 2 or 3 years left.
All but dissertation, as they say.
Yeah.
Well, you're off to an awesome start by putting out some APJ papers there, so that's really fantastic. So what do you like to do for research in general, Rosa?
So my focus is on binary stellar evolution, specifically the common envelope stage of evolution. Okay. So this is my primary focus for my whole PhD. It's a fairly small community that's working on it, and I'm coming from a different angle. Lots of people do sort of global scale simulations of the entire binary. I'm trying to look at how local simulations can help add information and can contribute in general, because the population synthesis community has been trying to figure out what tools are best for incorporating what we know about common envelope into population synthesis. And it's really hard to do that with what we're learning just from the global simulations because of some of the shortcomings that come with trying to, get better resolution and stuff like that. So I'm trying to be the bridge, and that's what I do.
Cool. That is awesome. That'll be a great PhD thesis. And that will bring us to this really lovely article. Common envelope wind tunnel, range of applicability and self-similarity in realistic stellar envelopes. Rosa, take us away.
Great. So common envelope wind tunnel, there's a collection of papers out there that sort of start with that phrase. It began with some work by Morgan, McLeod, and others starting in 2015 that originated from the problems in global simulations of common envelope evolution. So the biggest issue is that the physics in common envelope, which is when a primary star, which is going into its giant branch, engulfs its partner, is that the physics is on different time scales and physical scales that are across many orders of magnitude. This is a problem when you're trying to do a global simulation, obviously, when the same process can range in, for example, time scale from a few years to a few thousand years, and on length scales that go from, dealing with accretion on neutron stars all the way to a star that's puffed up to, say, 500 solar radii. So what Morgan attempted to do was to try to look at one stage of this. And this paper focuses on the dynamical in-spiral stage of common envelope evolution, also sometimes called the deep plunge or plunge in, which is when our secondary is deep diving into the envelope of our primary after it's been engulfed.
Okay.
So what the wind tunnel simulations attempted to do was to zoom in on the secondary during its in-spiral and see what kind of drag it's experiencing and what type of accretion is going on. So we were looking at this in a more zoomed in way, and trying to incorporate more and more physics into those simulations. And the idea was, as I said before, to be a kind of bridge between these large-scale global simulations and something that's more prescriptive, something we could give to population synthesis people. Cool. So Morgan had looked at some specific examples that were relevant to the community before, but what we wanted to find out was what is the broad range of applicability for this drag formalism that he came up with. So together with my collaborators, particularly with Morgan and Shomi Day, who was at Syracuse at the time, we were together at the Kavli summer program in 2017 in Copenhagen, and we're trying to figure out if we wanted to do a broad sort of range of different simulations to fill in the parameter space, we needed to know what that parameter space needed to be. So I'm not the one doing the actual 3D simulations in the box. That was Show-me's job. But what I did was I found this range of applicability that helped us decide what were the simulations that we needed to do.
Right.
Okay, so that's what this paper is really about. It's jumping off of the 2017 paper by Morgan McLeod and others that came up with a polytropic expression for trying to describe this. And what I wanted to see was when we use realistic stellar envelopes instead of polytropic stellar envelopes, what does that range look like in realistic envelopes, and how accurate really is the polytropic expression when we're looking at realistic stellar envelopes, because again, we are not actually looking at some of the standard structural values we're used to. There are specific dimensionless quantities that go with the wind tunnel drag formalism.
Okay.
Okay, so that's sort of the general background here. It comes from needing a little bit more of detailed simulations than the global setup could give us. A lot of work is still being done that's very good in that regime. We're trying something a little different. So the way we start the paper is by looking at different giant branch stars. So we use this broad range from, you know, 1 solar mass up to 90 solar masses, and wanted to look at what the envelope structure is like as we go through our giant branch. And the giant branch looks different in different mass regimes, as we know. But in common envelope, we tend to characterize a common envelope event by things like the mass ratio or the separation at onset. And what I wanted to show here in figure 1 is that for many given mass ratios and separations, you can have very different structure in your envelope. So we're looking at stars in different mass regimes. The contours of fixed radius are there that you can see. So for example, if we're starting our common envelope event at 100 solar radii, we could have any given mass ratio for these different primaries, and it's going to look a little different in our in-spiral because their structure is going to be different, because the way they evolve is different. So it affects everything from how much mass is held in the envelope, what the structure of the core envelope boundary is like. All of these things end up playing a role. So if we move on to figure 2,
Looks like
we are looking at,
all good.
Here we go. Oh, okay. If we move on to figure 2, we are looking at a selection of those stars when they've all evolved to about the same radius, which in this case is 250 solar radii. So they're all pretty puffy by this point. And what we're looking at is the rho T diagram of just their envelopes. So the cores are off the right-hand side. The limbs are in the lower left.
Right.
And we're looking at them overplotted on their gamma-3 value and opacity value. So the key takeaway from this plot is that we can see that these are not polytropic stars. We wanted to look at realistic stellar envelopes, and that's what we're getting. There are banded regions. Sometimes we get a mixture of radiative and convective bands. We see some density inversions and opacity bumps. There's a lot going on here that is pretty important to how their envelope structure looks. So that's what we're looking at. And these, and again, this is me saying, if we have some mass ratio Q and some separation A, we could have that with all of these different stars and we get a different in spiral because their structure is different. Okay. Yep. And we just go on a little bit further looking at some familiar structural quantities in figure 3, like density and sound speed, to look at how the internal structure is different in the different mass regimes. So for example, in the lower mass stars, you see a very clear core envelope boundary because you have this very steep area in the curve. Whereas in the high mass stars, you are looking for this peak in sound speed, for example. And you're also getting different ratios of the star's mass in the envelope for these different cases, again, evolved to the same radius. But when you look at them by radius, you can see, that they look very similar. The different sound speeds, of course, will give us different drag, et cetera, et cetera. But I'm just sort of hammering home my point here, which is that even with these sort of basic global quantities that we might set up for a simulation, you can't just use a polytropic star and throw it away. Like there are a lot of differences that we need to be thinking about. And something that is interesting about the drag formalism is that with the dimensionless quantities used, a lot of this extra information gets tied up in those dimensionless quantities. So it's actually a more thorough way of using a few quantities that tell the whole story, rather than going for our standard structural quantities, like density and sound speed, for example. Okay.
Good.
So moving along, we want to introduce you to those dimensionless quantities I keep referring to, right? Because in order to understand the results and be able to apply the results from Morgan's 2015 and 2017 papers and Shomi's mini simulations from her paper that came out this summer, we need to understand what these things are. So there's a few that we care about the most. One is Q, which is our mass ratio. There's two Qs that we use in this paper. We use QB, which is the global binary mass ratio.
Yeah.
And then we use QR, which is our local mass ratio as we're diving in. So Q binary is just going to be the secondary over the primary, which will always be, in general common envelope, you want it to be sort of less than 1. In our case, it's generally less than about 1/3.
Okay.
But that's because of the limitations of the drag formalism geometrically. And then QR is the mass of the secondary over whatever mass is remaining inside of its current orbit location. So that quantity is going to increase as we dive in, more dramatically as it approaches the core boundary. But we actually have a look at this later in the paper just to try to explain why we made the choices that we made. The next quantity we care about the most is our Mach number, which we've labeled M infinity. That is the velocity of the secondary during its in spiral, divided by the local sound speed. And in general, dynamical in spiral can be characterized with sort of a range of low Mach numbers. So in general, you'll see something like 1 to 5 or something like that, or 2 to 7, some range like that in any given in spiral. In our work here, we find it very rarely gets lower than 2, which is interesting, and I'll show you why in a moment. And the last quantity that we're going to see a lot of is epsilon rho. So epsilon rho is a dimensionless way of characterizing the density gradient in the envelope. And the reason we care about that is because in sort of old-fashioned Hoyle-Littleton accretion theory, when you have an object with a wind blowing against it of constant density, it has very efficient accretion. And in the past, anyway, a lot of work at Common Envelope sort of assumed this sort of Hoyle-Littleton style. And what Morgan showed in his previous papers was that when you introduce a density gradient, all that gets thrown out the window. Accretion is not really that efficient at all, and that it actually changes the drag force in significant ways because the symmetry is broken. You get this nice symmetric wake and shock when you're doing standard Hoyle-Littleton. When you introduce any density gradient, that just goes away. So how do we measure this? Our dimensionless density gradient, shall we call it, epsilon rho, is the ratio of the accretion radius, which is somewhat familiar. That's equation 4. That's sort of our gravitational sphere of influence of our secondary.
Mm-hmm.
So what this actually is a function of is not just our secondary's mass, but it's velocity, which ties in the enclosed mass of the primary as well as the separation of the two. So the accretion radius actually carries a lot of information about the system. And then we divide that accretion radius by the local density scale height at the location of the secondary. So when we look at epsilon rho, what we're actually saying is this is how many local density scale heights fit into our gravitational sphere of influence. So to make that a little more intuitive, if epsilon rho is 0, that's a constant density wind, just like standard old HLA, very symmetrical, okay? But any epsilon rho that's greater than 1 is going to give you a density gradient that is completely going to change the shape of the shock and is going to lower your accretion and all of those things. So, so it's interesting when we look at what our epsilon rho values are, because you can see that in any dynamical end spiral, we should assume that it's not symmetrical within this range anyway, with our mass ratio less than about a third. So then we look at equation of state a little bit, because again, we're not looking at ideal gas when you're talking about a giant branch star's envelope. So we just give a quick overview of how we describe it, because the previous 2017 paper did develop a polytropic formalism based around what we call a structural gamma, which is how would we calculate the gamma if we assumed this was an ideal gas based on its structure, versus the actual equation of state, adiabatic indices that tell us how it's going to react. So basically, if we're looking at an envelope, oh, sorry, Frank, you might be muted.
No, I'm good.
Okay, sorry, okay. So basically, if you're looking at either an ideal envelope or an envelope that has constant entropy, all of these gammas will be the same. And that means all of the sort of analytical work from the 2017 paper can be applied. If that's not the case, then that's pulled into question. So that's why it's important to give a look at those. So if we look at figure 4, this is sort of showing, this is the visual version of what we've been talking about, which is trying to show those different gammas, that gamma S is the structural gamma that's calculated from the actual the structure of the envelope rather than an equation of state value. On the left-hand side, we're looking at a 3 solar mass star that's at 31 solar radii. And what we can see is that those gammas tend to be more or less the same. So that's probably a convective envelope. It's got pretty much constant entropy, which is why they're all the same value. And what we would expect is to see a Mach and epsilon rho value here that increase monotonically from the inside to the outside of the star. And more or less, that's what we get. So this is what we would expect anyway. When we look at the massive star here, so if we look on the right, that's a 50 solar mass star extended to about 400 solar radii. And we see different behavior with the equation of state there, because we're dealing with banded regions. We've got, we've got radiation pressure. We've got all these other things going on in this more massive stellar envelope. So we don't share those values. It's not constant entropy anymore. However, we do still see that gamma 1 and gamma S are the same most of the time. And what I found interesting when I was first looking at these plots when I was beginning this work is that if you look at our Mach and epsilon rho values, again, you more or less see the same type of monotonic increase, even though we see that very dramatic drop in the structural gamma in our top panel. That translates to this tiny bump in our Mach and epsilon rho values. And what this clued me in on is that maybe if those issues are sort of smoothed over in Mach and epsilon rho, there's a possibility here that we can actually apply this more broadly, even though it's not an ideal gas and even though we're not at constant entropy. So I wanted to explore that further.
What are the gray bands?
Oh, yes. Okay. So what the gray bands show is the span of an accretion radius if your secondary is at the location of a dark gray line. So these are just 2 examples per panel. So for example, if our secondary is at the dark gray line on the left side in the left-hand panels, then the stretch of its accretion radius is to the left and to the right in the dark gray regions, and so on and so forth.
Okay.
What this was meant to give you a sense of is how much do these quantities change inside of an accretion radius.
Okay.
So
Good, thanks.
okay, so now what is the big takeaway from the simulations, from the local wind tunnel simulations that we are trying to apply more broadly? So each simulation gave us these coefficients. So there are drag coefficients and there's accretion coefficients. And they're basically just multiplicative factors that you add, that you multiply the Hoyle-Littleton version of what you would expect for accretion or that you would expect for drag based on the local structure. And you multiply them by these coefficients to get the results we got in the 3D simulations, in the wind tunnel simulations. Okay, so what this means is that if you have this big parameter space full of your accretion coefficients and your drag coefficients, you should be able to actually give a prescriptive description of any particular dynamical inspiral if you have the structure of the primary, right? Because you can calculate all these quantities from any good stellar model, right? And so then we want to apply these coefficients and actually be able to model inspirals using these results. So that's just sort of described in this little section of text, what they represent, and that we multiply the drag coefficient by the HLA drag force. We multiply the accretion coefficient by the HLA m dot. Yep. Okay, so this is just how you would apply those coefficients from a practical standpoint. One exciting result that came out last year is that a paper by Luke Chamandy and others, I believe they're at Rochester, were working with global simulations of common envelope and actually compared the drag force in their simulations to these drag coefficients from previous work by Morgan McLeod and others, and found that during dynamical inspiral, as it should be, they were in very good agreement. So, so that inspires us to keep moving forward, right, and to continue developing this formalism. That was a very encouraging result. So, so great. We have all of our background. We have how we want to apply it. Now we need to actually figure out what is the parameter space that we want to do all these simulations in. What kind of coverage do we need to actually create some kind of prescriptive formalism here? So, okay. So in section 4, we start mapping these different in-spiral setups into this parameter space. So the parameter space is basically using the Mach number and epsilon rho, and then our mass ratio Q. So in what we see going forward, you'll see some plots where we use Q of the binary, which is to help you keep track of what the initial setup is for our in-spiral, and some that look at the local Q, QR, so that you can actually see how much that changes during a given in-spiral. Okay. And our assumptions here are basically going through almost the entire envelope except the very outer limb. That's not always going to be the case, as we know. In different situations, onset looks different. So if you're looking at a Darwin tidal instability, you might dive through most of the envelope as it is, whereas if you have a very messy onset with mass loss, etc., you could lose a lot of this. So to stay sort of open-minded and just cover the full parameter space that we might need, I just assumed that we would keep most of the envelope. And then it's sort of up to whoever's trying to utilize this to figure out, based on their mass ratio and based on their setup, are we dealing with a very messy onset? Are we dealing with a tidal instability that maintains most of the envelope? So, okay, so here we go. So what we're looking at in figure 5 is 2 different stars at different parts of their death, basically. So we're looking at different radial extent. So the radial extent is approximately the same as we go from left to right, but we're looking at a 10 solar mass star on the top and an 80 solar mass star on the bottom. And the color represents where we are in that particular star. So it's R over R star. Okay, and what we're looking at here is just dynamical in-spiral. We're not looking at the full star, including the core, etc., because we're only trying to map the in-spiral, the dynamical in-spiral. So we're starting at the upper right-hand side, which is the edge of our star. That's the beginning of our dynamical in-spiral, and we're going all the way down to the bottom left. Okay, so that's the direction that we are diving.
Okay.
And as you can see, a large span of the characteristic curve in this parameter space that we're showing is really the very outer regions of the star. So what that means is that you cross a lot of range in Mach number as well as in epsilon rho in those outer regions most of the time. And as you approach the inner part of the envelope and you're starting to get closer to the core, you actually cover a smaller region, a smaller span of Mach and epsilon rho. What that means is if you are going through dynamical in-spiral after a very messy onset and have had a lot of mass loss, it's very likely you're going to be going through a very small region of Mach and epsilon rho. Whereas if you're dealing with a Darwin tidal instability, you're going to cross a much wider range, and that means you're going to have very different types of drag as you're going from the beginning to the end of this dynamical in-spiral. So that's going to be a very interesting looking in-spiral. One of the other things that you'll note here is that in these two stars, we're sort of crossing the same area of parameter space over and over again, right? They look very similar, and honestly, these are very characteristic of almost all the models that I looked at. So it looks like a lot of the same. This isn't what we expected when we were looking into this, because we just weren't sure, especially dealing with very different radial extent, how different these would be. And you can see that there are small sort of blips and bumps here and there that are representative of, for example, shifts in gamma, or for example, you might see some banding regions and things like that. But the question is how much of this comes out in the wash when you start looking at a lot of these models. So I'm sort of leading you through my thought process in a way.
Good.
So if we move on to the next figure, figure 6,
okay.
What this looks at is one primary star, but looking at different global binary mass ratios. So the color here represents the local mass ratio, QR, and then the binary mass ratio is shown in each panel. So this is for the same envelope, just a different secondary. And what we can see here is that there's a slope dependence on our binary mass ratio. So we are dealing with a wider expanse in what we would call our dimensionless density gradient when we have a larger mass ratio. Now, why would that be? Basically, it has to do with the fact that our accretion radius and the velocity that we're going to be coming in at are going to be affected by that different mass ratio. But if you think about just having a wider accretion radius, of course, that's going to cover more local density scale heights, right? So it's actually very natural that we would have this slope dependence on Q. Something else I'd like to note is that you can see that for most of the dynamical in-spiral, at least within the parameter space, QR stays fairly constant. Now, if you look at the paper that Show Me Day did, sort of in tandem with this one that also came out this summer, the way she treats a lot of her in-spirals is she just assumes Q to be constant. This is why. It's because for most of that arc and that characteristic curve in parameter space, we have a pretty constant Q, even if we're following local Q instead of that of the binary. So that's the reasoning behind that.
Okay.
Okay.
That helps.
All right, so we're looking at these characteristic curves. We're looking at what regions of parameter space they move through, and we're starting to notice that there's a lot of similarities even when we're dealing with very different models. Okay, so if we want to move on to figure 7.
Okay. Yeah.
We can look at figure 7 and 8 at the same time. Yeah.
Okay.
So, so what are we looking at here? We are looking at different primaries that are all at about the same radius, about 250 our sun. And we're looking at the characteristic curves for those different models for different mass ratios, different QBs, different binary mass ratios. And again, what we're looking at here is that these cover about the same area of parameter space over and over and over. So am I hammering my point home?
You are. I got it.
And upon looking at these sort of beautiful fans that they create, I began to ask myself, like, these are realistic stellar models that have more going on in the envelope than a polytrope. But they all look like they are extremely self-similar. And I thought, what if we try to collapse these down? So if we look at this new quantity, which I've called epsilon rho q, which is dividing your characteristic curve by the local q term.
Okay.
That's in the polytropic expression from the 2017 paper. They collapse beautifully into this into this line, right? But they collapse into such over and over and over again. So I said, okay, what if I look at everything I've got in these two ways? So what we see in figure 9 is 50,000 stellar profiles in these two parameter space panels. So on the left, we've got Mach against epsilon rho. And on the right, we've got Mach against epsilon rho q. So those are the collapsed versions of these fans, which is to say they've been calculated with all of the q values and then divided over that term. And you can see that the parameter space is very clearly outlined, and the simulations that Shomi did for her paper are in brown. So you can see all those brown dots that cover that parameter space very nicely. And I would say even go further, because as we found in this work, dynamical in spiral rarely makes it down to Mach 1, but we even have simulations that are down in that regime also. So the idea is that we have all these simulations that cover this parameter space and can be applied, because anyone can calculate the characteristic curve for their in spiral of choice, plot it in this parameter space, and then they have the coefficients for drag or the coefficients for accretion that they need to model that dynamical in spiral. And what was more exciting to me that sort of looks at future work is that in the right-hand panel, if we have this very nice clean line of this collapsed epsilon rho q curve, does that mean that we can actually take that curve and expand it again? Does that mean if we have that curve, we have the gamma for the equation of state for our stellar envelope, and of course we have our collection of coefficients, can we actually take that line, give us some very basic information about our star, and actually open that fan back up? Right. And do a prescriptive characteristic curve? So that's really exciting to me. And that's the next step that we're taking this on in our paper we're working on.
What are the colors? You've got gray, purple, bluey.
Okay.
What is the color scheme here?
So all of those colors are actually blue. It's just, okay. Yes, it's just, I would say Matplotlib's ability to render when it's very translucent. Okay. So I would say the most intense blue is where you have a lot of concurrent characteristic curves, and where you see this sort of wispy gray feathering, you have a few characteristic curves that go in that region. So I would say that's the best way to read this plot.
So it's kind of measuring the density of the characteristic curves? So
that's right. Okay. That's right. So, so this was very exciting to me and showed me that there's a lot of self-similarity in these curves, There are some exceptions, of course, which we start going into in section 5. But in general, this to me showed very promising that this is something we can actually extend forward, especially with a few other additions, which we talk about later, to try to create something that's more prescriptive, something that maybe population synthesis people could use someday. It's not as simple as, say, the alpha energy formalism. It does require things like fitting functions or interpolating values, depending on which approach you want to take. But it's still far less complicated than actually having to analyze every single primary stellar profile or to do a 3D simulation. You don't need any of those things if this relationship holds.
Yes.
So in oh, sorry, go ahead.
No, I'm good.
Oh, sure. Okay. So in section 5, this is where I talked about some of the issues with this. Like, when does it not work, right? When does it not hold?
Right.
And basically, it's like the stranger the envelope is, the less this is useful, right? So if we're dealing with a very strange equation of state, or we're dealing with a large number of bands that are sort of switching back and forth within your accretion radius, so there are little things that still, I would say, need to be worked out. One of the main ones is being able to understand how we can deal with different equations of state in the same envelope. Because if it's only happening a little bit, if we're getting sort of little bumps, it seems like, especially across an accretion radius, it's not that big a deal. It sort of comes out in the wash. But when you're dealing with larger scale differences in structure, that, and especially density inversions, that is an issue. So you can't really use the wind tunnel drag formalism at all when you're dealing with density inversions, because you get a negative epsilon rho. Yeah. And of course, that it just doesn't fit. But something that I would assert is that as more studies on onset are being done, it looks to me like the regions in which density inversions take place, first of all, it could just be like a 1D, 3D thing, but also during onset, those areas could be stripped or their structure shifted anyway. So my take on it is that it's not something to worry about right now, but that you should probably, if you're trying to apply it right now, you should probably stick with profiles that don't have density inversions, or make sure that you do a very detailed treatment of onset. There are some more recent papers that came out that talk about how much mass loss might occur if you're dealing with an onset that's a little more messy. And what we found is that if we actually apply some of those prescriptions, you lose all the density inversions and they go away. So
yes.
So that seems fine. One of the other interesting things that came out of this was what we call the dynamical boundary. So there's been a lot of conversations, because the transition from dynamical in spiral to self-regulated in spiral has been really difficult to model, because it can take a long time. And also seems like it depends on things that not every global simulation takes into account. So what is going on there? And when can we apply this and when can't we? So the wind tunnel formalism was developed specifically for the dynamical in spiral. So any attempts to use results from those simulations in self-regulated in spiral naturally don't work. You can see this a little bit in Luc Charmandy's paper from last year that did that comparison, because you can see where the dynamical in spiral ends, and then we start sort of having this regulation starting to occur, and then the coefficients don't match what he measured. Of course they don't, right? Because it was developed for dynamical in spiral, which depends on having undisturbed material that we are going through. When you start to reach self-regulated in spiral, structures having time to change on the thermal time scale, we've got like all these different things happening at once. So when you actually look at the undisturbed structure of the profile, there's this location where you can see that the characteristic curves sort of naturally come to an end as they're approaching the core. And it's not the core envelope boundary, so I want to be really clear about that. And it's also not the bifurcation point that we might assume if we were using an energy formalism to see like where we would expect the envelope to become unbound or something like that. It's not that. What it's actually doing is looking at the structure of the primary envelope and asking, when are the Mach and epsilon rho values appropriate for this actual dynamical end spiral, and when would it stop because of these quantities. So what you actually will see if you move to our next figure is a study of what the dynamical boundary is and isn't. So you can see that the dynamical boundary, which is marked in dark brown, always occurs before the core envelope boundary. The core envelope boundary is defined in a number of different ways. It's been explored in other papers. There's not really a great answer, especially since in different mass regimes, the core envelope transition looks pretty different. But here are a couple ways it's been described in the past. For example, H1 mass fraction, or entropy, or nuclear burning, for example. Where you see, well, I guess I should say, the outer edge of the star is the blue diamonds, so then we're going outside in as you trace the lines.
Yep. Outside in. Yep.
Right.
Yep.
So when you look at the blue markers and the X's, those are ways that we would look at, for example, core envelope. Well, the blue markers are what we'd call the core boundary. The X markers are where, for this particular star, energy formalism would tell us we had a bifurcation point, or we would unbind the envelope. And we can see that the dynamical boundary is outside of those regions all the time. What we think is happening is that because the gravitational sphere of influence, our accretion radius is a bit broader, it's that we almost like run up against the core envelope boundary before we get there. It's like our sphere of influence runs into the core before the secondary does. And we think that has a lot to do with why we end up self-regulating, you know, that close to the core, right? Is because we actually don't have conditions that that work for dynamical end spiral, basically. So we've looked at that in our curves, and in general, it comes at or near the lowest Mach number, though this can change if we have a very complex envelope that has banding and stuff like that. But I'd say for the simplest case that looks like a typical characteristic curve, it happens at the lowest Mach number. And it really is just a measure of the fact that the accretion radius is bouncing up against the core, and we're going to start to slow down because it's harder to scoop that material out gravitationally than it is the envelope that we've been going through recently. Okay.
Okay.
Moving along. Okay. Let me make sure I'm hitting everything. Okay, yeah, let's just move to the next. Right, okay. So here in the next figure, this was sort of looking at what happens when our characteristic curve goes off the rails, and why does that happen? So in cases where our characteristic curve does not look like the typical one, what is happening? So we can see for our characteristic curves, you look at the lower panels, that's our Mach epsilon rho space.
Yep. And
what I've plotted above them, they're just matched color to color. So a red curve at the bottom matches with a red curve at the top. So we're looking at what's happening in the equation of state and when that connects to oddities in our characteristic curve and when it doesn't. So what you'll see in the upper curves when we have some of these sort of roller coaster hills is we're looking at banded regions. We're looking at we're looking at radiative and convective regions in bands. And if you look at the very outer edge of the star, you can see these big spikes. Those are density inversions. What's interesting about the characteristic curves that go with these is that sometimes you don't even see these banded regions at all, but what you see is the density inversion.
Sure.
So for example, you see this big red spike in the first panel on the top, and you see a nice spike into negative epsilon rho in the characteristic curve on the bottom.
Mm-hmm.
The only thing that shows that something's off is that we have that density inversion. And all the other funny stuff going on in the equation of state is not even showing up in that bottom curve.
Right.
More so, if you look at the rest of the characteristic curve that goes beyond that spike from density inversion, it actually fills the same parameter space as the other more typical curves. So that to me is interesting and points to, again, what I said before, which is that if we were to implement some type of onset scheme, and if this star actually experienced some mass loss, we might not even visit that part of the characteristic curve in our dynamical in spiral. So this may still be useful, just not in that region of the star if it's retained. So it's important to take a look at that. We also have some higher mass stars. We have a 16 solar mass, which is intermediate mass, and then our 50 solar mass. And you can see that those characteristic curves have some interesting things going on also. So you don't get the same shifts between convective and radiative, but you do have gammas that don't really fall into like the 4/3, 5/3 category. And it's when you get these sort of intermediate gammas that you get these characteristic curves that have all these curly cues and things like that. So namely, the purple curves that you see on the bottom correspond to having gamma values that are sort of intermediate between gamma 4/3 and gamma 5/3. So I would say if you're trying to implement this right now and your profile looks like these curly cues, maybe that's not the one to use.
Okay. Fair enough.
And then last but not least, in figure 12, what I was really trying to show is about the equation of state and whether the ratios in the polytropic expression from the 2017 paper would actually be relevant across this wide expanse. So what are we actually looking at? Again, this is all the same profiles as before. And we're looking at them in Mach epsilon rho and Mach epsilon rho q, but the colors correspond to gamma 1 over gamma s.
Mm-hmm.
This ratio tells us basically how constant is our entropy, or is it close to constant, or can we at least use the prescription that assumes that it's constant. And though, of course, there's some breadth to this, still the majority of curves end up showing gamma 1 over gamma s of 1 or close to 1. And what this tells us is that we can use the polytropic expression in a somewhat prescriptive way and still be in the right ballpark. Again, there are times when it doesn't totally apply. We can see some of those profiles feathering off to the left and to the right. But when trying to develop something for population synthesis people, we're trying to get to what are the best generalizations we can get when we actually look at the whole range of parameter space that we might use. So I would say there's still work to be done. It is possible that we might need some simulations that span a bit more of a range of gamma, for example, to make sure that we have coverage in that space as well. But to me, this looks like a good start, and I'm ready to start experimenting with it basically to see what we can do. So what do we need to move forward with a more prescriptive semi-analytical treatment of common envelopes? So we need something that goes beyond just dynamical in spiral, right? This is one phase out of 3, 4, 5. So we need a similar type of treatment for onset, something that can look at the same global properties and tell us what type of onset do we expect, how much mass loss are we going to get or not get, and how is that going to change our separation at the beginning of dynamical in spiral, for example. We also need a treatment for the transition from dynamical in spiral to self-regulated in spiral.
Okay.
and that's going to be a little bit more difficult to do. But again, if we can get it, what we're trying to find out is, the question isn't just how does the envelope eject, it's when does it eject, and what is the secondary doing while it's ejecting. You know, we talk about dynamical ejection, where we're able to eject the envelope during dynamical in spiral, but we also see a lot of cases in which we assume, based on the outcome of our global 3D simulations, that ejection is happening during self-regulated in spiral at some later time. So we just need to look deeper at that. But you know, our group is doing some work on that right now, and the hope is that if we can come up with a similar type of treatment, we can translate the results from that into some sort of semi-analytical form, and build a nice little framework for population synthesis people.
Very cool. Very cool. Should be an awesome thesis.
Yeah.
Awesome. Rosa, I want to thank you so much for spending some time today and taking us through your paper on common envelope wind tunnels.
Thank you so much, Frank. I enjoyed it.
I did too. All right, everyone. Thank you so much, and we will see you on the next one. Bye-bye.